Hi, my name is Rajan Sharma. I'm a switch architect at Broadcom. Today we're going to look at one of the innovative aspects of the NPL language, which is the ability to enable runtime network programmability. We define runtime programmability as the ability to make significant data path changes to a networking device without modifying the NPL code or having to load a new SDK image. Now we're going to look at what this means in some detail, but before we do that, let's try to understand why runtime programmability is important. Over here, we've shown the three main steps in delivering a feature for an NPL capable device. There is the NPL app development, followed by the network OS development, followed by the actual deployment. The key observation here is that in the general case, multiple organizations and teams are responsible for these various steps. So the NPL app may be developed by the silicon vendor or by the network OS vendor. And the network OS itself could either be done by an OEM, or it could be a third party or an open source network OS. The most important part here is that the end user who deploys networking devices in their actual networks is most often not involved directly in either the NPL development or the network OS development. At the same time, end users have strong operational and business needs to customize switches and routers for the specific needs of their networks. So this is where runtime programmability comes in. And what we feel makes NPL a unique language in this space. Because NPL has constructs and capabilities not just for the NPL application developers, but actually for the end users who want to leverage programmability and customize things in their real-world networks. So let's look at three of the runtime capabilities in the NPL language in more detail. So first, let's look at dynamic tables. So NPL has two types of logical tables. There's static logical tables, where the NPL developer has to specify in complete detail how the key for the lookup is constructed, what types of objects are returned from the table lookup as policy, and also the conditions under which the table is looked up in the first place. With static logical tables, if there's any change needed, that of course means a source code change and a recompile. But there are also dynamic tables, and these have built into them a great degree of runtime configurability. In the case of dynamic tables, what the NPL developer specifies is templates. And templates can be thought of as menus. So there's one template that has a list of various possible objects that could be used as part of the key. There's another template which is used to specify all the possible things that could be part of the policy. And finally, there's a third template which has all the possible conditions that might be needed to decide whether to do a particular lookup at all. So the best way to understand this concept better is to look at a real-world use case for dynamic tables, which is access control lists, or ACLs. As we know, ACLs tends to be an area where there is a wide diversity of requirements. Some network engineers prefer to implement their ACLs with IP prefixes and layer 4 addresses. Others may prefer to use layer 2 information and VLANs. Yet another organization, for their needs, may need to use a combination of IP layer 4 and layer 2 information. So it becomes impractical to try to support all these kinds of variations with static logical tables. And this is where dynamic tables become very useful and powerful, because the NPL developer creates menus with some forethought in terms of all the things that would be useful for end users. And then the end user, at the time of actually deploying and configuring their switch in their network, can pick from these menus. They can choose the specific things they want to use in their key, in their policy, and to decide how to do the lookup. So dynamic tables allow all of this configurability without requiring any NPL change or an SDK image reload. So the second feature we're going to look at is dynamic table resizing. Now this is also a fairly simple and intuitive feature. The basic concept here is that with NPL, the end users have a significant degree of flexibility in deciding the sizes of various logical tables in the application. So for example, an organization that's running a mostly layer 2 network may wish to maximize the scale of their MAC tables. On the other hand, another organization that's running a mostly IP network or a layer 3 network may wish to have just a small MAC table and have a much larger IP route table. So with NPL, this kind of resizing flexibility is again available at runtime to the end users. And at a language level, there's a fairly basic primitive concept that enables this. Whenever an NPL developer creates a logical table, they specify a minimum and a maximum size. So it's not just one size. And then the compiler and the SDK leverage this information to create a framework in which end users can change table sizes within these limits at the time of deployment. So with NPL, end users get a lot of flexibility in terms of deciding how to deploy hardware resources to maximize the logical table sizes and features that they are most interested in. So the third feature we'll look at is runtime instrumentation. With networks becoming ever larger and more complex, instrumentation and visibility are key features for any networking device. And perhaps more than any other feature, this is an area where end users really need the ability to configure and fine-tune the kind of information that's collected, the triggers under which information collection happens, the way the information is packaged and exported from the device to their collection framework. NPL has many constructs related to instrumentation and visibility, and all of these constructs have runtime programmability as a baseline requirement. So for example, there is a construct called packet trace. So this is a construct that the NPL developer can use to flexibly identify any interesting situation that they want to use as a trigger for some kind of data collection. And so when a compiler encounters a packet trace invocation in a program, It of course maps it to some hardware resources, but it still allows the SDK to retain control over how exactly that trace event is processed. So through the SDK, the end user can decide whether for a specific packet trace event, it triggers a counter update, or it generates a copy to CPU, or it generates a copy to a mirror destination. Or it could be any combination thereof. So the end users retain a lot of control over fine-tuning how and when information gets triggered in their live networks. And this is pretty standard across all the NPL instrumentation features. Now let's summarize. We looked at some of the runtime capabilities in the NPL language, and hopefully also got a sense of why these capabilities are important and powerful. So if you're interested in learning more about this or other NPL topics, there's a lot of useful information at nplang.org. And if you're interested in deploying runtime programmability in your actual networks, then the Broadcom Trident 4 and Jericho 2 devices are both NPL and runtime programmable. There is more information about these devices at the Broadcom webpage. Thank you so much for your time.